periodicity is just a fancy way of talking about using the periodic table to follow patterns. So those periodicity are just patterns on the periodic table. That's really all that, when we say that term periodicity, that's all that means, okay? So one of the things that we're going to, there's basically three different topics we'll talk about that deal with patterns on the periodic table: ionization energy, sizes of atoms, atomic and ionic radii, and what's called electronegativity. This is a review from first year chemistry. We're going to get into a little bit more detail here. So let's dive right into ionization energy. So ionization energy is defined as the energy required to remove 1 mole of electrons, so 6.022 times 10 to the 23rd electrons, from 1 mole of gaseous atoms. So how much energy it takes to take away 1 mole of electrons from a mole of atoms. So here's a fake element M. So notice it is a gas, it is a gaseous atom, and then it becomes M plus, and then you've lost an electron. And this here represents the first ionization of element M. Okay, if you're talking about the second ionization of element M, then you have to start with M already having lost 1 electron, and now it's going to lose another electron. And now you can see it's lost that second electron, and again, this here, this equation represents the second ionization of M. And yes, that's been on the AP test before, where they've said, write the chemical equation that represents the first ionization of whatever element. So you should be familiar with that. Okay, notice that the energy is written in terms of kilojoules per mole. Again, not a big deal. Notice that they are both positive values, though, and ionization energies are always positive values because it always takes energy to remove an electron from an atom. Okay, we'll talk about the increasing number in these in tomorrow's video. Okay, now, how much energy it takes, or what we refer to as the magnitude of the ionization energy, is determined by 2 things. And imagine this, the 2 things are the 2 things in Coulomb's law. They are, number 1, the number of the charge. Remember that Coulomb's law, the force of attraction, is directly proportional to the charges divided by the distance. So the one thing that determines ionization energy is the nuclear charge, or easier said, how many protons there are. The more protons there are, the greater this charge is, and the greater that force of attraction. And then the second thing is the distance between the nucleus and the electrons being removed. Okay, and again, notice these are both parts of Coulomb's law that you should use to describe these patterns on the periodic table. So, number 1, here is a poorly drawn periodic table. As you go across the periodic table from left to right, what does the ionization energy do? The ionization energy increases. It goes up. And why? And notice the italicized part is this is how you would describe it on a test. Because what are the things the grader's looking for? The number of protons increases, okay, and the valence electrons are in the same shell, so the distance are very similar, okay? A greater number, and again, that's what they're going to be looking for. Does the person talk about the increase in the nuclear charge? Does the student talk about how their valence electrons are in the same shell, so that distance between the nucleus and the valence electrons is basically the same. Okay, and then just some more detail here. A greater number of protons increases the attraction to the nucleus, and since those valence electrons are in the same shell, more energy is required to remove an electron from an atom that has more protons in it. Okay, for example, look at sulfur, which is right around here on the periodic table, and chlorine right around here. They're in the same period, okay? And so that means that sulfur's valence electrons are in the third shell, the 3s and the 3p subshells, and so is chlorine. But chlorine has more protons. And so since chlorine has more protons, those electrons are more attracted to the nucleus, making it, you require more energy to take an electron away from chlorine than you do sulfur. Okay, as you go down a group on the periodic table, so as you go down this way, again, the first ionization energy, in this case, decreases. Okay, and really there's only one thing you need to talk about here, is that the valence electrons, as you go down the periodic table, the valence electrons are in shells that are farther away from the nucleus. So there's more shielding due to those more core electrons, we call them, or inner shell electrons, and are therefore held less strongly. I realize there are more protons. As you go down the periodic table, you're increasing the protons, but in this case, the distance is the bigger factor. So when you go down the periodic table, you always want to talk about distance being the deciding factor. Really, as you go across the periodic table, because the distance doesn't change much, it is the charges, it's the number of protons that makes the biggest impact. As you go down the periodic table, though, what makes the bigger impact is that distance from the nucleus out to those valence electrons. Okay, so example number 1 here. Which element has a greater first ionization energy, aluminum or phosphorus? Justify your answer. So this would be a good time for you to pause the video, write out your answer, and then restart it again and wait for me to give my explanation as well. So, which one would have a greater first ionization energy, aluminum or phosphorus? Aluminum's number 13, phosphorus is number 15. They're in the same period, so I would say that phosphorus has the greater first ionization energy because phosphorus atoms have more protons. So the attraction to the nucleus is greater in phosphorus, and both atoms' valence electrons occupy, reside. Again, there's no perfect way to say this, but there's so many correct ways you could say it. Reside in the same shell. So the greater, and you could actually stop there, greater number of protons makes the difference. Again, I probably wouldn't, now that I say that, I probably wouldn't say that part. Okay, so phosphorus atoms have more protons, so the attraction to the nucleus is greater in phosphorus, and since both atoms' valence electrons reside in the same shell, phosphorus is going to require more. Okay, example 2. Explain why the first ionization energy of polonium is less than that of selenium. Okay, so polonium, again, look at where they are on the periodic table first. Where is polonium compared to selenium? Polonium's farther down the periodic table. Again, don't say that. Just like up here, I never said that phosphorus is to the right of aluminum on the periodic table. If you do that, you will not get credit. Okay, if that's all that you write is, phosphorus is farther to the right, so the attraction's greater, they will not give you credit for that answer. You have to talk about it in terms of protons and electrons. So same thing here. You can't say polonium's lower on the periodic table. Okay, what you can say is that polonium has more electron shells. Okay, and so the valence electrons in polonium are farther away from the nucleus than in selenium, and so the attraction is weaker. Okay, and so the attraction is weaker, it requires less energy. Okay, and so up here you're really looking for two things: the more protons, okay, and valence electrons in the same shell. You're really looking for two things when you're going across the periodic table. When you're going down the periodic table, and you could even be more specific. You could say that polonium's valence electrons are in the, off the top of my head, I don't know, but let's say in the 5th shell, where selenium's is only in the 3rd shell. Or you could even be more specific. Polonium's, last subshell is the 5p subshell, where selenium's is only the 3p subshell. And then again, say that's farther away from the nucleus, so that means a weaker attraction. so less energy to take an electron away from. Okay, so here we can see this is kind of just a graph that shows that as you go across the periodic table, what does the ionization energy do? It goes up. Across the periodic table, from left to right, it goes up. As you go down the periodic table, you can see from helium down to xenon, what does the ionization energy do? It goes down. Now you will notice a couple of spots here where it doesn't follow that trend. Okay, here's the D subshell. Do not worry about the D subshell at all. Okay, we're just talking about the S and the P subshells only, nothing else. Okay, but you do see a little drop here when you go from the 2S and the 3S subshell to the 2P and the 3P subshell. But then you also see another drop when you go from like nitrogen to oxygen right here, and the same thing happens right here. Okay, let's talk about why that happens. First of all, from the 2S to the 2P subshell, you're going from S2 to S2P1. Okay, the P subshell is at a higher energy level than the S subshell is. Okay, so the P orbital is a slightly higher energy than the S one is, and is slightly further away from the nucleus, so you have a little bit more shielding. Okay, so therefore it's easier to take that first electron away, because that first electron you put in that P subshell, again, is a higher energy orbital. It's a little bit further away, and it's shielded by those S electrons. Again, probably not going to see a question about this, but just there has been one. It was actually about oxygen, the oxygen and sulfur, but they technically could. Okay, with oxygen and sulfur, what happens is it's easier to look at the orbital diagram. Okay, nitrogen is 2p3. Okay, and phosphorus is the same thing. Phosphorus is 3p3. But with oxygen and sulfur, what has to happen is now you've got 2p4 and 3p4. Okay, and this electron, right, it goes right here for, now we're at oxygen. Okay, so this electron that's being removed, which is this one right here, is paired with another electron. Okay, and electrons, remember, do repel each other. Okay, so because these two electrons are paired up and they do repel each other a little bit, that electron is more easily lost than an electron, for example, that's all by itself in its own orbital. Okay, those electrons a little bit harder to lose, but now that you've paired it up, that one electron there is a little bit easier to take away because of that repulsion between those electrons. Okay, and that is what we are going to talk about with ionization energy today. We will continue. We're going to talk about ionization energy a little bit more tomorrow as well.